IB wants us to know about some common magnetic field patterns. So let's look at some of these, right? A solenoid, and this is an ideal solenoid, right? Even with the windings closer together, right? A solenoid is our magnetic equivalent of the parallel plates for a uniform electric field, right? If we wanted to generate an electric field, we just have this like a capacitor or something like that, right? Okay. With a solenoid, inside a long, narrow solenoid, not near the edges, but in the middle, right? Right here, there's this beautiful uniform magnetic field. Notice that it all points this way. When you do this lab, I've got these little magnet probes. Stick them inside there and then show that they're all parallel. These lines are beautiful. They're parallel. It's very uniform. Um, to the extent that the coil has, lots of gaps between the windings, or to the extent that you're near the edge, that breaks down a little bit. Okay. I remember in physics in my undergraduate, there was something called, I think they're called Helmholtz coils, where you could sort of get a uniform field. You'd have a multi-winding flat solenoid like this, and then another one like this, right? You picture that, and then there's a space in between them like that. They would face each other. This would face this face here, right? Kind of like this. Lots of windings, lots of windings. And I think if you space them, their radius apart, or maybe their diameter or something like that, you'd get a fairly uniform magnetic field in there. But anyway, there you go. So a solenoid is just like a coil. Okay, inside the coil there's a uniform magnetic field. Remember that you wrap your fingers as the current, right? And then your thumb is the direction of the flux. It's also the direction that the North Pole is, right? Here's the North Pole, here's the South Pole, right? But anyway, there you go. The second one is a long straight wire. Okay, now the problem is that of course you have to have a circuit, so every long straight, our long straight wire is just one side of a big solenoid, right? But with this thing, right, remember you put your thumb this way, right, in the direction of the current, and your fingers will wrap around the wire. So on this side of the wire, it's into the page. This side of the wire, it'll be out of the page. And again, take your magnet probe, put the current in that multi-strand wire up to about 4 amps, 5 amps, right? And just see that it actually does. It actually goes in a circle. The magnetic field is actually circular. And of course, the magnitude of this field is from Ampere's law, right? U naught I over 2 pi r at some distance r, if we look at a spot like that. Anyway, and then the final thing is flat circular coils, right? So imagine that this is a coil. This is the thing we've got, only it's not circular. Ours is rectangular, but that's okay. Basically, your magnetic field is highly ununiform. It's basically like a donut. It's like a donut. Do I spell it that way? Donut. No, it should be, the nut shouldn't be like N-U-G-H-T. There we go. Anyway, donut. Let's spell it that way. Anyway, it's very donut-like. Okay, in the plane of the coil, it'll be all in one direction, but it diverges, right? Notice that these field lines, they all loop around. We're just not drawing that one, but that one loops around. This one goes to Vermont before it loops around, right? Okay, good enough. Enough